Progress.
Yeah, ask questions at any time, because I don't want you to lose the thought. All right. So I have a very tentative schedule, and again, this is going to be based on how quickly we move through the material. Some of us are familiar with dyadic data. Others of us probably haven't had any experience with it. So I'm going to go at the pace in which kind of the group learns. And so my intention is to get through, 6 or 7 different variants on the common fate model and the actor partner interdependence model, but that we might not get through it all. And so I've intentionally kind of set aside some of the models that we're not going to get to. And if you want to learn about them, then you'll have to take my class next semester. But this is going to be the tentative schedule. We're going to go for about an hour and a half in the morning, take a 15-minute break, and then go till 12. And then we'll have lunch on your own. And then we'll do the same thing in the afternoon, about an hour and a half, and then take a break, and then finish off the day with another hour and 15-minute lecture. And then I've set up time at the end of the day. I'm calling individual consult time. If you have any questions, or if you just have questions, you have dyadic data you don't know what to do with, or if we didn't get to something and you want me to teach more about it, I'm fine going an extra hour. It's kind of really flex time for us to get through whatever we need to get through. So day 1 is structured. We're only going to be doing the APIM today. I don't think there's any way we're going to be able to get to the common fate today. So that's going to be tomorrow. And we might end up doing a little more APIM in the morning, depending on time, where we will do some within dyad analyses, because as in family science, at least, we don't do a very good job at differentiating within and between analyses. We actually do a really terrible job, in my opinion. And so we are going to spend some time talking about within dyad analyses. All right, so again, I think this is redundant information, but that's where all the program files are. So I'm going to kind of give you all a brief overview into kind of my framework for this workshop. This is not going to be an extremely deep dive where we're going into matrices and we're going deep into equations or anything like that. This is more designed for the applied user, so you can get familiar with dyadic analyses and better understanding how we analyze interdependent data. And then from there, there's lots of really good resources. Dave Kenny has a wonderful website. Him and Tom Lederman and his colleagues Deborah Cashy have written numerous articles where you can take a deeper dive. So again, it's going to be an introduction to kind of a more moderate approach to these dyadic analyses. All right. So I want you to be able to articulate dyadic principles. So that's how we're actually going to spend our morning. It's a review or introduction of SCM, and then we're going to be talking about dyadic ideas. And then we're going to be moving in the second half of the morning, hopefully into the active partner interdependence model. We're going to be talking about measurement a lot, because again, I think that's something we do sometimes really, really well. And I think sometimes we just pretend it doesn't exist when we use sum scores. So I'm going to be talking a little bit about measurement within a dyadic context. And then we're going to talk about 2 different models. And then we're going to learn when to use one and when to use the other, compare and contrast them, and what research questions they can answer. So again, this can be focused far more on the conceptual ideas of dyadic data rather than, again, that deep dive into these equations and matrices and all those things. You will see some of those things in the slides, but we're not going to spend a whole lot of time talking about it. All right. Another kind of a key aspect is we're going to be focusing mostly on distinguishable dyads. All right. So I'll talk more about what that means in a second, but essentially there's a way we can distinguish partner 1 from partner 2 from a theoretical basis. But we also have indistinguishable dyads like identical twins. That tends to be less common in our work. So I will focus mostly on indistinguishable dyads, and then there will be code and syntax provided for indistinguishable dyads along the way, and we might, depending on time, we might run a few analyses with indistinguishable dyads. This slide deck is 30 megabytes. It's a behemoth. There's 545 or something like that. I'm not going to try to get through 545 slides in 2 days. This is almost a semester's worth of material. And so we're probably only going to get through 300 of them. And a lot of them are just pictures of M+ syntax. So I've given you more than we're going to be covering so that if you want to do a deeper dive, you certainly can, right? But I want you to at least have that information and then be able to go do some more research again on your own. So you will see me feverishly clicking that right arrow button as we skip through slides. So don't be alarmed, and it's intentional by nature. Any questions? Yeah.
Wait, just how big do you think it's capable of? There is coffee and bagels over there that I think is up.
Yep. So we're gonna do a couple slide review on Stats 101. We're gonna spend a little bit of time talking about linear regression, because I'm actually going to be assuming that many of you have a background in linear regression, have taken Psych Stats 1 and 2 or REMS 1 and 2 or some version of that. All right. But for those of you who need a refresher or perhaps aren't there yet, we'll do again a brief dive. So just think back to, this might even be undergrad stats, thinking about the contribution of two independent variables in the prediction of a dependent variable. All right, so we all know that our variables have variance, right? Average squared deviations, right? And so in our dependent variable, what we're trying to do is we're trying to test whether or not our independent variables, 1 and 2, are a significant predictor of variance in our dependent variable. All right, and so we can have our first independent variable predicting variance, our second independent variable predicting variance, and then we can have what's called shared variance between the independent variables, where they're both accounting for the same variation in the dependent variable, which is indicated by B. All right, so what we see in the diagram is A is the unique variance accounted for by IV1. B or C is the unique variance accounted for by IV2. B is shared variance, and D is error variance. Everything that is left over that isn't accounted for by either independent variable 1 or independent variable 2. And so what we have is we have partial correlations, and so that's A and B, and also B and C. And then we also have semi-partial correlations, which again is unique to each of those predictors. And so again, this is just basic linear regression. Now let's think about this in the context of dyads. What if instead of IV1 and 2 being two separate independent variables that one person is reporting on, what if it's two different people? And so when you have single reporter studies, you're capturing either A and B or B and C respectively, but you're not accounting for B in some ways because you don't have that second dyad member. So that could potentially result in an overestimation of the actual effects because we're not accounting for those partner effects. And so single reporter studies have the potential to be, quite biased in terms of the nature of the associations. And so that's one of the reasons why we need dyadic analyses. So put it kind of a little more colloquially, I have how well I think I communicate, and I have my partner, how well they think they communicate. Well, how I communicate is probably going to influence how happy I am with my partner, but also how well my partner thinks they communicate. That's probably also going to influence me in some type of way. So if we're only estimating my effects, again, that's going to be way overestimated, okay? Or has the potential to be way overestimated. So again, this is one of the rationales that we need in dyadic research. And so we have linear regression. So linear regression is probably one of the first techniques. You probably go in t-test, ANOVA, and then probably went into regression. All of them are part of the general linear model, which is subsumed within the generalized linear model. That's why people hate learning statistics from stuff like that. And it's kind of like that very first car you have. That's how I view linear regression. It's that old beat up station wagon. It kind of works, kind of doesn't, but you're not exactly, you know, beaming with pride, but it does the job, right? It's efficient. It does exactly what you need it to do. And it's a closed form of estimation. And it's relatively simple to understand. How do we employ linear regression? Well, we try to minimize the sum of squares residual, right? We're trying to minimize those residuals. That's really easy. We're trying to find regression coefficients that minimize those residuals. That's really straightforward. The math behind it is a little more complex, but it's a fairly simple concept, right? And so that's great. That's wonderful. And we make a lot of assumptions to get kind of that ease of understanding. All right. And so we make numerous assumptions. And this, by the way, is not all of the assumptions, but it is some of the assumptions that we make. So the distribution of your IVs are fixed and known. All right. So that's kind of confusing. Essentially, that means there is no measurement error. So we assume perfect reliability on our independent variables in linear regression. All right. We all know that's not true. And so that's where we are kind of living in denial. That's where we're kind of putting our hands over our ears and saying la, 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 while we make this assumption, right? But we all know it's not true. You are linear in the parameters. So a lot of people, this is where it can get a sticking point for people, that is where your beta 0, your beta 1, your beta 2 are linear. Your IVs like X and X1, X2, X3, X4, they do not have to be linear. All right. You can have age and you can have age squared as a predictor, and that doesn't violate any of the assumptions of linear regression. Okay. So you're linear in your parameters, in those beta weights. Okay. Multicollinearity is not a major issue. I hate to spoil it to you. If I see something in a discussion section that says multicollinearity is a reason I found non-significant findings, I'm going to be like, probably not. Because if multicollinearity was actually a big problem, your model wouldn't converge. All right. So you're going to find, I'm actually going to show you an example of that today, I think, where I tried to fit one of the models. It's for our between dyads moderation. We have covariances among the predictors that they're at like 0.93. There's like 3 or 4 of them that way. So we're going to walk through the model as if it converged normally, but we'll actually see what multicollinearity looks like. But you don't even really approach multicollinearity until your predictors are, 0.90, 0.95, and then there's several of them. All right. So multicollinearity is not a reason you didn't find significant findings. Residuals are normally distributed. That's another one where people can get a little hung up. A lot of times they look at the marginal distribution, your distribution of your means or whatever it is, and they say, oh, it's not normal, or it is normal, so I'm fine. When really it's the assumption is in the residuals. Okay. And then residuals are independent of one another, and that's the kicker in dyadic analysis. All right. We assume that my residual and your residual, if we're in the same study, they provide only unique information. If you know something about my residual, you don't know something about your residual. All right. But in dyads, that's not the case. And so moving into structural equation modeling, that's the Lamborghini of the world. It's my personal favorite car. It's my dream car. It's a car I'll never be able to afford. Beautiful car. It's highly flexible. Everything within the GLM and generalized linear model is subsumed within SEM. Okay? And now SEM is now being subsumed within dynamic SEM, which is a combination of time series multi-level modeling and SEM. So everything you've already learned in first year grad stats or in undergrad stats is an SEM in some way, shape, and form. All right, we can conceptualize it that way. All right. And so multiple regression. Here is a path model of a multiple regression, and that is an SEM model. And if you have no missing data, if you throw that model into SPSS and use OLS, and you throw it into M+ or Procallis or Levon, you're going to get pretty much identical estimates. There'll be some differences due to rounding errors and in the ways that different statistical programs estimate things, because they have different assumptions actually, but you're going to get the exact same thing. They're identical, all right? You also have independent samples t-tests. You just have group and then you have your DV, right? That's an SCM model. We just don't necessarily think of it in that way. Your ANCOVA, same thing. You have your grouping variable and then you have a covariate predicting your Y1, all right? Repeated measured ANOVA, the exact same thing. You have your grouping variable and then you have Y1 at time 1, and then you're regressing that onto Y1 at time 2, all right? So everything you've already learned is an SEM in some forms, or relatively simplified SEM. And so I've already talked about this a little bit, but in OLS, the way we determine the best model is by minimizing those residuals, right? Minimizing those sums of squares residual. And so that's great. That's awesome. And it's simple, works well. It doesn't really handle missing data all that well, but that's a different issue for a different day. But in SCM, we're going to kind of flip that on its head a little bit, all right? Instead of minimizing the residuals, we are trying to maximize the likelihood that our model represents population parameters, all right? So rather than minimizing something that's within our data, we're trying to maximize the likelihood that our data represents what we believe is actually happening out there in the real world, all right? This is you will see throughout today and tomorrow, I will go off on several diatribes on certain aspects of models. And if you've ever taken a class with me, you know I do this a lot. So I'm going to try to keep that to a minimum. Your OLS regression, you are not testing your hypotheses. Sorry, because whatever you throw in there, that's the model. You have no control over it, right? You're only rescaling your means, your variances, and your covariances. You're moving those means up in your mean on your Y up and down the number line. You can't constrain passive equality. You can't say this predicts this, which predicts this. You're not actually testing what you actually want, because model fit in your regression is your R squared. Is that really model fit? Is that really testing how well our hypotheses are doing by the amount of variance explained? I mean, to me, not really. That doesn't feel like we're actually testing something. It feels like it's just kind of like an outcome of us just throwing a bunch of stuff into a model, all right? And so that's why I like the SEM. It's because in the SEM, we can do a whole bunch of really cool things where I think we're actually testing our model, right? Another way of kind of thinking about this is going back to like the multiple regression, here you have 0 degrees of freedom. You are estimating the same number of parameters as you are allowed to, all right? And that's another reason why I don't believe you're testing a hypothesis, right? Here it's completely saturated model. All your IVs are correlated with one another, and all of them predict your DV. All right. So what are you actually testing here? But in SCM, what we can do is we can actually test how well our model fits our data. You can't do that when you have 0 degrees of freedom. You just can't. It's not possible. And so what we can do is we can constrain pass to be 0. We can constrain pass to equality. We can do all sorts of really, really cool things where we're actually threatening our model in some way, shape, and form. That's what I think we need to do as scientists, rather than loving our model and being attached to our model. We need to put it in mortal danger. And because to me, that's what good science is. It's because if we're just testing our models the way we think they are, then we might be wrong. I can't tell you how many analyses I've been wrong on, and they haven't come out, and that's okay. I learned something from that. So you learn just as much from being right as you do from being wrong. And I even argue you learn more from a little more about a little more about research and things like that from being wrong. So in the SEM, we're allowed to do this. And we're allowed to do this, again, in a lot of really, really cool ways. And so in SEM, one of the benefits is that we have what's called a whiteboard problem. I can say, and anyone in here, you can come up and I say, what is your diagram? What is your model? And you can come up and literally draw it on the whiteboard. All right. And it can be, you could have 2 variables, most likely not, or it could have 10 variables or 15 variables or 20 variables, but you can come up and you can draw it. And then I can ask you, is X1 really related to Y, or is it only operating through that mediator? And so if you say, I think it's only operating through that mediator, then guess what we can do? We can pluck that relationship or that path from your independent to your dependent variable. All right. So in SEM, we can come up and we can create these really elaborate models. That's also where we can, it can get dangerous. We can overfit our models. We can just throw about 30 different predictors in there and just to see what's there. So there's a lot of opportunity for misuse. But in SEM, we really have the access to the full whiteboard, which we do not in linear regression. All right. So we can have complex models like this. This is my first author publication. It's a dyadic longitudinal cross-lag actor-partner interdependence model. In ML in multiple regression, it has no idea how to understand this. It can't. What you can do in multiple regression is you can have this right here, these 4 variables. And then after that, it taps out. It's like, I don't know, it's too much for me, man. All right. In SEM, we can do very fancy stuff like this. Another benefit of SEM is we can, again, truly make our models testable. We can truly say, this is a non-significant path, or these 2 paths are equitable. And it allows us to really, again, put our theories into dire risk, right? The caveat to that is we can go a little too haywire sometimes. So let's say we have a really complicated model. So if we even go back to my model, is what you see here is I'm hypothesizing that none of these emotional abuse, physical abuse, and sexual abuse prior to 12, they are not predicting relationship quality at 14, 16, or post-traumatic stress symptoms at 16, right? And so I'm going to have some degrees of freedom, but let's say my model is saying, hey, maybe emotional abuse is actually related to PTSS directly. It's saying it's what's called a modification indice. It's popping up saying, you know what? This is actually related to this. That's what the model is telling me. And so I see that, and I might include that path and re-estimate the model. But if I do that and I just simply take that data-driven approach, research has shown if you just use those modification indices that your SEM, every SEM model will give you, you never get back to the correct population model. Ever, 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 ever. All right. So be very, very careful around these data-driven approaches. Again, that's far beyond the contents of what we're going to talk about today. But this happens all the time in confirmatory factor analysis and latent variable modeling, where residuals want to correlate with one another. And we're going to see a little modification index. And the model saying, hey, this is how you fix your model. This is how you make it a little bit better. But we need to be very, very careful about that. Yeah.
Is that just
essentially, yeah. It's saying that there's the potential for your chi-square to go down by about 10, and because of there's an unexplained associations and sorry, I just lost my train of thought. Yeah, and then because every model is going to have nuances between those errors. So that's exactly what you're doing. You're overfitting, and it has to be theoretically derived, in my opinion. And I think that's a lot of the problem with it. So yeah, you're overfitting to error. Yep. So again, that's one of the beauties of SEM, but that's also one of the downfalls of using SEM is well-intentioned researchers can see my model doesn't fit all that well and just throw paths and paths and paths and paths and paths on it, and nothing really, you don't really get to where you need to be, all right? Okay, so now some more explicit benefits of SEM. I don't know about you, but I find people in academia, they like controlling things. They like knowing how things work, because that's why this, in part, probably that's why this career was attractive to you in some way, shape, and form. And so when you're in a multiple regression, you have no control. Yeah, you can throw whatever variables you want in there, but you're at the mercy of how the variables relate to one another. It is what it is. Same thing with exploratory factor analysis. You throw all of your variables in there, and what happens is what happens. Right? But when you move into the SEM, when you move into a confirmatory factor analysis framework, you can exert control. Again, that's where I talked about constraining paths to equality, omitting paths. You can even set paths to a specific beta weight. If you're that confident in the relationship between your IV and your DV, you can say this path is exactly 0.24. Right? You can exert all of this control. Likewise, you're actually testing your hypotheses. You're actually testing how well your model is reproducing your data. Right? You're in multiple regression, because you have 0 degrees of freedom. You're not doing that. Right? And then this is the big one. The big benefit that I see in SEM. And that is latent variables. I'll go on a small diatribe later on, either this afternoon or tomorrow, about latent variables. But essentially and no one can agree. First thing I'll say is no one can agree on what a latent variable actually is. I'm a Ken Bolin guy, or Ken Bolin guy. So I think it's literally anything that is not measured in your data file. All right. And you talk to a biostatistician, they're like, latent variables are not a thing. Hey, what's your residual, buddy? Is that observed in your data file? No. All right. So latent variables really, in my view, really do exist. And so they're anything that can be subsumed within your, that's not measured in your data file. So that can be an overarching factor, right? So when we think about depressive symptoms, for example, can we just go out and can we pick up depression and hold it in our hand? Not really, no. Can we go and just look at someone and just say they're depressed? No, not really, because we can't directly observe it. What do? We give them the CESD, we give them the BDI, we give them the PHQ-9, and we begin to infer depression's existence from responses on things that are actually measured. All right. And so we're saying depression exists, and it's indicated by problems with mood, problems with cognition, losing weight, poor sleep habits, thinking about death and dying, suicidality, things like that. All of those are proxies for the construct of depression. And what SEM allows us to do, it actually allows us to get at that construct, all right? And it allows us to get at that construct without measurement error. And again, we've already talked about in linear regression, there's measurement error in all our variables, right? So SEM really allows us to attenuate and get rid of that. And so our parameter estimates are actually going to be more accurate because we can overestimate or underestimate our parameters in linear regression, all right? And so when we think about our introductions and our discussion, what are we talking about? Let's use the depression example. We're actually talking about the construct of depression, right? We are not talking about depressive symptoms. We are not talking about these individual symptom profiles. We're saying depression, right? And so when we say depression in our theoretical background section, when we say depression in our literature review, and we talk about why it's important, we're not, and we use like a multiple regression, we're not actually measuring depression at the level we are talking about it. And so to me, that's a problem. That's just introducing error into our models. Okay. And so this is some, for those of you who have read Jacquard and Jacobi, just a classic text, highly recommend it. What they argue is that we actually, by using latent variables, is we can actually get at these ideas. We have our conceptual definition of what depressive symptoms actually are. We have our focal concepts within depression. And then we have our latent variables, a proxy for those, for that conceptual definition and that focal concept, right? So this is where face validity comes in, and this is where content validity comes in, all right? That's in between focal concepts and proxy. And then what we can do is we can create questions to assess those different domains of depression that we believe to exist, and we can test how well those items kind of cluster together and are an indicative of that latent construct of depression, right? So again, you can't do any of this in multi-level modeling and linear regression. And sometimes you are just modeling measurement error. I've seen some studies where there's Cronbach's alpha is 0.50, 0.60. So if it's 0.50, half of your variance is error. And that, I don't know, that scares the crap out of me. Honestly, how can I trust those parameter estimates if half the reason people differ is because of just random error? So again, latent variables allow us to kind of parse that out and kind of get rid of that so we can get those more accurate parameter estimates so we don't run into type 1 and type 2 errors. Actually, I'll stay here. So essentially, this is the simplest, relatively speaking, latent variable model. For those of you who are visual, we have our construct up here of 801, which will be indicative of depression. And then we have our different items. So we can have suicidality over here. We could feel negative mood over here, and we could feel disturbed sleep over here. And then how well the individual items of depression, how well they are related to the overall construct is indicated by these factor loadings right here. Lambda 1, lambda 2, lambda 3. All right. And we generally want these to be above 0.70 on average. Some people say as low as 0.40. That's to me way too low. 0.70 is good. But essentially, it's a quantitative indicator of how well our items are indicative of the construct that we believe to exist. And then we have measurement error here. All of our items, we don't, because they're dependent variables, our observed items are dependent variables within SEM. We believe that there's error associated with that. There's unaccounted for variation, method variation, variation around testing. Perhaps you get some cross-loadings. Depression is highly comorbid with anxiety. So maybe some of these depression items actually load a little bit onto like an anxiety factor. And so we can pull that out of there. And so our means and our variances of our latent factors are going to be more accurate, right? Another benefit of the SEM is multivariate outcomes. You can actually trick multi-level modeling into doing this, but it's a little more difficult. It's a little tenuous. But in SEM, it is a natural strength that you can have one dependent variable. I've done that. I mean, I've had studies where I have 6 or 7 dependent variables. Simple mediation model, but I had 7 outcomes, right? And OLS regression, not a chance. You are running 7 different regressions for that, right? And don't even get me started on multiple testing. That's a potential really problematic. And so that's another great benefit of structural equation modeling is those multivariate outcomes. We also have formal tested mediation, right? In MLM, you can kind of allude to mediation, but it's still tenuous at best. But in SEM, we have some really great methods. We have delta method, we have the Sobel test, which is we have bootstrapping, which is and then we have robust maximum likelihood and other things like that. So in SEM, we have a lot of different ways to examine those indirect effects. And then we have, this is gonna be one of my diatribes, we have fit statistics. So in multi-level modeling, you have your deviance or your -2 log likelihood, which we have here, but that's only a relative fit index. So you can compare nested models, but you can't really compare model 1, which has 6 predictors, and model 2, which has 7 predictors and a level 2, because those log likelihoods are not going to be directly comparable. And so you have, again, a saturated model, and so you can't really evaluate to the extent to which it fits. So you can do a likelihood ratio test in your multi-level model, and you can say, I'm going to add 1 predictor, and I'm going to see if it fits any worse, and you get a significant difference test, which is fine, well, and dandy. It's great, but your model could still suck. Because there's no actual indicator of how well your model fits your data, you might be saying model 2 is better than model 1, but that's a really relative statement. Model 1 could have been horrible to begin with, and model 2 is just a little less horrible. But in SEM, we have a bunch of different fit statistics that evaluate the extent to which our model actually fits our data. And that's where we get the degrees of freedom. That's where they come in. And so we have our chi-square test, which is the traditional, that's where it all started back in with Yorskog and Lisriel and all that. And then the CFI and the TLI. We also have the GFI, the normative fit index, and we have all these other ones that people use in order to evaluate the extent to which our hypothesized model that we put on our whiteboard actually fits what is actually happening in the data, all right? So that's the good news, is we have 5 or 6 or 7 kind of well-established methods of saying, this is how well our model is doing. The bad news is these fit statistics kind of suck. And we don't teach you this in SEM because we want you to get comfortable with SEM, and we don't want to scare you away, but they suck. In low degree of freedom models, your RMSEA is either going to be 0 or it's going to be 0.2. And if you just use that routine cutoff of 0.06, you could be rejecting a perfectly fitting model. It could be a beautiful model, but it's just because there's low degrees of freedom, right? I've had models where I've had a CFI of 0.87, and it was actually a beautiful fit to the model, because all of our fit statistics are going to be based on the number of degrees of freedom, the extent to which our models covary with one another, whether or not they're latent variables and things of that nature, all right? And so I still use these global fit indices, but I also incorporate local fit indices, which are essentially the extent to which my parameters are over or underestimated compared to where the model believes that they should be, all right? So to me, I take like a gestalt approach. And when I'm for example, when I'm doing CFA with latent variable with only 4 factors, I don't even report RMSEA because it's going to have 3 degrees of freedom or 5 degrees of freedom, and it's completely biased, right? But in those models, I'll report local fit indices, I'll report CFI, I'll probably report the chi-square and things of that nature. So don't be drawn in by the allure of CFI above 0.95 means good fit, because that Hu and Bentler paper has 30,000 citations. 29,998 of them are wrong. And because Hu and Bentler, they did a 2-variable confirmatory factor analysis with the loadings of, I think it's like 0.6, 0.7, and 0.8. Is that the exact same thing as a path analytic model where you have 7 observed variables and mediation? Not even close. So people have overgeneralized. Hu and Bentler and Klein has some fit statistics and all of those things. So just be really, really careful around fit statistics. All right. And again, I've cited Hu and Bentler incorrectly. This is not a holier than thou. It just means learning is an ongoing process. And all of the things that I say not to do today and tomorrow are going to be things that I've most likely actually done myself. All right. So it's more about the knowledge is power and being aware of what is actually happening. All right. And why things might be appropriate and why things might not be appropriate. Oh, and the local misfit. This is available in every SEM package. It's just not common output. So you'll see it when I get into M+ today, it's called the residual. In Lavaan, I know it's there. I can't remember the code, but I've run it in Lavaan as well. So you can absolutely request these other forms of fit indices to evaluate the extent to which your model fits your data. Okay, so there's going to be 6 major steps in SEM. Before I refined the PowerPoint, I used to go through each step on 2 slides, but I'm already going to be long-winded, so I'm going to spare you from my diatribe on each specific step. But essentially, it's you have your specification, which is your whiteboard, right? You specify your model. You draw your diagram, your path diagram on your whiteboard and say, this is my model, all right? And so the next step is to ensure whether that model is identified or not. Because you can have local or empirical under-identification, and you can have kind of more theoretical under-identification where you have negative degrees of freedom and your model will not run if you have that. So you have to be sure that you're rescaling your means, your variances, and your covariances in an appropriate way in which the model will let you do. And then you estimate. This is where you choose maximum likelihood, or this is where you choose robust maximum likelihood, or you use a link function, or you do any number of other things to tell your software program in what way am I going to analyze my data, all right? Evaluation. So you create a theoretical model, you realize it's identified, you're good to go, you choose the right estimator, most likely maximum likelihood, and then you evaluate your model. You use fit statistics, you potentially don't, I argue, do not look at your p-values the first time you run a model, because then you're potentially biasing yourself because you're revising your model based on a p-value, not based on fit. All right. So the first thing I do is I go to the fit statistics. Right. Then you make modifications. Again, as I talked about before, modifications are an integral part of SEM, but also they're dangerous in a way, because that's when I was talking about you can't get simulation research says if you just follow the modification indices, then you never get back to the original population model. All right, and that's highly problematic. And you're playing a game called whack-a-mole, where you hit a problem down in one aspect of your model and it's going to pop up somewhere else, right? And then you modify your model as appropriate, and it should be in a theoretically driven fashion, all right? So I don't have a slide on this, but I was running measurement invariance on a relationship quality measure. And there was the modification indices. They said there should be a residual covariance between 2 of the items. All right. And so I went through every modification index that the SEM package gave me, and I looked at the extent to which it changed my data, because I want to figure out, is there a mole here that's poking his head up? And there was one mole who needed to come out, who needed to be accounted for. And so what I did was I went back and I looked at the actual items. And I said, is there a reason or a rationale or a justification for correlating the residuals on these 2 items? And it turned out there was a method effect. It turns out they were phrased in a way that was fairly consistent with one another, and that wasn't the same as all the others. And so I was comfortable adding that modification index after the fact. But do you know what I didn't tell the reader is I hypothesized that a priori. And that's what most people do in SEM. They make modifications to their model and they say, this was my model all along. And no, it wasn't. It's called, in SEM, it's a confirmatory technique. What you're doing by modifying your model and saying, this was my whole model all along, that's not confirmatory, right? That's exploratory. Okay. And then once you get a good model, you can move on to interpretation and actually look at your p-values, your standard errors, your parameter estimates, your direct, your indirect effects, your moderating effects, and things of that nature. All right. So returning to our Lamborghini, sometimes we have a Lamborghini in the garage. It's great. Sometimes you don't need one. do I want to take my Lamborghini down a pothole-laden street just to pick up a few things at the grocery store? No. No. My station wagon will do just fine in a lot of these different circumstances. But in the context of dyadic data, our station wagon is essentially a no-go because it doesn't do independence of observations, it doesn't do multivariate outcomes. There are just a whole lot of problems associated with it. So a Lamborghini for our purposes is absolutely what is needed. I didn't know where to put this slide. I couldn't figure it out. And SEM use wide format, where on each line, you are going to have a dyad, all right? And then you're going to have the male partner over here and then the female partner over here. In long format, you would have dyad ID, and this would be 1, 1, 1, and you have female, male, female, male. But in SEM, we use wide format, all right? Again, kind of a non sequitur, but I couldn't, for the life of me, I couldn't figure out where to put this. So recommended readings, if you do SEM, you need to read Mullen's 89 book. It's a must read. It's phenomenal. It's technical, but it's actually very accessible. It's not written in an academic fashion. To me, I can read it, and it's generally tends to be fairly makes a lot of intuitive sense the way he presents the material. But again, it is focused on, there are a lot of formulas, a lot of equations. And so if you want to get experience in SEM, you got to read that book. Handbook of SEM. I'm making my way through that right now. Another great book. And then Timothy Brown's 2015 book on confirmatory factor analysis. That is probably the most clearly presented book on confirmatory factor analysis that I've ever read. It is beautifully laid out. All right, so highly recommend that book. And then if you're looking for M+ specific, Wang and Wang have a book that came out in 2019. All right, so that was, again, a brief, half an hour run through what I think should be 3 sequence stat classes in grad school. Only most of you will only get 1, maybe 2. That's actually something I want to create. I want to create a SEM2 class where we go over the categorical stuff, but that's another talk for another day. So now we're going to shift into dyadic data. So why you guys are actually here. You didn't come here to hear me yammer on and whine and complain and moan about all the things that are wrong with SEM and OLS regression and things of that nature. But if you're in the psychology, if you're in the human sciences, if you're in public health, even if you're in medicine, in some ways, you study relationships. You study the therapist-client relationship. You study the doctor-patient relationship. You study the relationship between parents and children, or couples, or even education, teacher and student, or teacher and teacher, teacher and principal. Right. So dyads are the foundational unit of analysis for a lot of us, but we either don't collect the data in a dyadic way, or we kind of collect the data, but we aren't really sure how to analyze it. And that's what we're going to be talking about for the rest of today and tomorrow. And so the theoretical ideas underpinning dyadic data originally come from interdependence theory by Kelly and Thibault in the late 70s. I think it's a phenomenal, I think it's a book that I've read, probably 4 or 5 chapters of it, a really decent book. But I think the need for dyadic data is better presented in the context of family systems theory, right? So I realize not everyone has training in family systems theory. You may have had like an undergrad lecture in it, but it's essentially the idea that you cannot understand any one person's behavior without understanding the context in which that behavior occurs. So you could look, when you're fighting with your partner, you could look at it and say, hey, you yelled at your partner right there. And you could easily go into a psychological explanation about that. You could use some Freud to do some psychoanalysis. You could try to figure out why that is. But from my perspective, I also need to know, why is that person yelling? What did their partner say before that? How did their partner respond after that? That, to me, is the core of understanding people's behaviors. What is the context behind the behavior? Because if it turns out that they just found out their partner cheated on them, that to me presents an entirely different story about why they're yelling compared to if their partner just walked in the door, right? So context behind behavior matters. And so that's what I'm kind of alluding to is kind of sequence of interaction where A causes B, causes C, causes D, right? And so in order to understand D, you have to understand A, B, and C. Otherwise, you might be missing something. And in statistical phraseology, that's a misspecified model if you're not capturing one of those, right? There's also another idea in family systems theory that says the whole is greater than the sum of its parts. So you'll see the equation elsewhere in the PowerPoint, but 1 + 1 = 3. All right. In family systems theory, you have person 1, you have person 2, and then you have what exists between person 1 and 2. Right? Because you can't just look at person A's neuroticism and person B's neuroticism. It's how their neuroticism plays off of one another that contributes to these outcomes, right? And that, again, can't be captured in other frameworks. And so people are going to have varying levels of what I've described thus far as called interdependence. They're going to have varying levels of interdependence. So my students are going to be a little bit interdependent with me, right? Unless I do something absolutely outrageous, I'm probably not going to have a huge impact on their overall positive affect or negative affect. Might have a little bit of an effect, or if it's a dissertation or a thesis meeting, might have a little bit or a lot bit, but it's temporary, right? But you also have to think about, for those of you in a relationship, you have a lot of interdependence. When your partner walks through the door and they've had a bad day, they don't have to say a damn thing, and you know something's wrong, right? So there's shared meaning, there's shared experiences, there's a relationship history that is there, and again, that's what's called interdependence, right? And so what we're doing in dyadic data is we're modeling that interdependence, but we're going to do it in kind of 2 primary ways. And you'll hear me talk about what's called correlatant. All right, those are the 2 different ways kind of smushed together. Right. So from a dyadic data perspective, individuals are nested within their relationship. Right. Students, a classroom of students are nested within a teacher. All right. Kids are nested within a family. All right. Neighborhoods are nested within a community, right? So you have these smaller units that are interdependent because there's a higher order second level unit at play, right? And so the problem is when you use like OLS regression and you have non-independent data, if I have my residual, I have your residual, but if they're correlated, which means if you have my residual, you know a little bit of something about your residual, that downwardly biases your p-values and your test statistics and your standard errors. All right. Actually, it downwardly estimates your standard errors and your upwardly biases your test statistics and your p-values. So it's a type 1 error. All right. And so sometimes this isn't a major problem. I've run analyses where, I have a data set of 3,000 people, and there's 600 twins there, and I account for the standard the interdependence, and I don't account for the interdependence, and nothing really changes, right? There are going to be those situations, right? Because the research question isn't focused on interdependence, or the number of people who are non-interdependent far outweigh the people who are interdependent. But I've also had analyses where if I don't account for that, my values go from p = 0.02 to p = 0.15 after I account for the nesting, after I account for the clustering of those people, right? And so again, this is not just a, let's be academic and talk about statistics and, be in our ivory towers. This has real world implications for all of you people who are going to be running analyses. And if you don't account for the non-independence of your data, that can lead to big time problems and erroneous conclusions. Right? So that's again, reason number one why we need dyadic analyses. So even if you don't have a dyadic question, even if you just have interdependent data, you need to be able to think about these types of things, right? Or perhaps account for them in some type of way, right? So that's reason one. Reason two is this opens up a whole new set of questions, right? We can now look at how partner one contributes to partner two and how partner two contributes to partner one, and we can look at that back and forth, all right? With just a single reporter data, you can do that, but it's not all that accurate, right? As we've already talked about. And so this opens up a whole new field of research questions that are more nuanced, that are more powerful, and that, to me, in my eyes, have greater external validity. Because when we think about just modeling individuals and we're asking them about relational processes, is that really kind of what's going on in their relationship in the real world? And my argument is a little bit. Sure, absolutely. But you want to be more accurate, you want to be more precise, get the partner's perception too. All right. And that way, that's going to be far closer to what is actually going on in the real world, so to speak. All right. So actually, I'm gonna skip over these slides. All right, so we have two primary models that we're going to be going over today and tomorrow: actor-partner interdependence model and the common fate model. And they account for interdependence among dyads differently. All right, so what you'll see is, if you've ever seen a cross-lag panel model, the base APIM looks exactly the same thing, same specification, same everything, really. It just, the interpretations change just a little bit. And so they account for the interdependence through a correlated residual, which we're allowed to do in the SCM, because we're allowed multivariate outcomes, and through partner effects. So essentially how I affect you and how you affect me. That is how the actor-partner interdependence model captures that non-independence. In the common fate model, we bring in those pesky latent variables, and we are going to say that there's a level two, a dyadically oriented process that is happening that is causing my partner to respond the way she is and causing me to respond the way I am, right? So for example, dyadic coping. We're going to go through this example actually in a little bit more detail a little later on. We have kind of dyadic coping and what it looks like in between us, right? So what is actually happening between us? Because dyadic coping is inherently a dyadic construct, right? So we have my reports and we have my partner's reports. And so according to the common fate model, there's a latent variable that's dyadic coping at the relationship level, what's occurring between us, and that's causing my responses, and that same latent variable is causing my partner's responses, right? And again, it's going to be it's kind of hard to wrap your head around, especially with the common fate model. It tends to be a little less intuitive than the actor-partner interdependence model, but that's what we're going to be doing all day tomorrow for the most part. So hopefully by the end of the workshop, you'll get a grasp on the common fate model, but it does take you a while, because unless you've had really intensive family systems training, it's probably not something you've talked a whole lot about. So this is where I came up with correlatant. You account for interdependence through correlations, which is the APIM, and the latent variable, which captures a dyadic level process, which is in the common fate model, okay? All right, so there's going to be several types of dyads that we can have, primarily going to be two. So we have what's called distinguishable and indistinguishable dyads, all right? And so distinguishable dyad, okay. Before I go into that, because on the next slide, the reason that this is important, it has implications for how you specify your model. You specify your models differently if there's a way to theoretically differentiate partner A and partner B. There's implications for power. All right, so you actually have more statistical power in indistinguishable dyads. You need fewer dyads to detect the effects, all right? Because they're actually going to be presumed to be equal, right? And there's also significant implications for theory. All right. And I'll talk a little bit more about that here in a minute. So you have indistinguishable dyads, which are like same-sex twins, monozygotic twins. And so they're both male, both female, they're both whatever it is, they share 100% of their genes. They're essentially identical, right? And so assignment to them to a dyad member A or dyad member B is completely random. I can say twin one, you're going to be in your dyad B, your partner B, and twin two or twin one, you can be dyad A. Doesn't matter, right? For most of the time, there are going to be some research questions where it does matter. So it's completely random, it's completely arbitrary. Or you can have distinguishable dyads. And distinguishable dyads is you have a theoretical rationale and a variable in your data set that says, hey, you are going to be a dyad member A, you're going to be dyad member B. So if you do couples research, gender versus biological sex, that's a distinguishing variable. We're saying all the males are on this side and all the females are on this side, right? So that is that's a distinguishing variable, and we have theoretical rationale to distinguish dyad members that way. We have gender socialization, we have any number of other rationales for saying why we want to look at differences between men and women in relationships, right? And so we have that theoretical rationale. Are there any questions about that? About distinguishability, because that people can get hung up on distinguishability sometimes. Okay. So you have theoretical indistinguishability, and then you have empirical indistinguishability, or distinguishability, however you want to say it. So, yeah, sure. Sure. Yes.
Same-sex couple.
Yeah. It does. So I'm going to get back to that question a little bit later, either this morning or this afternoon. But if I don't, ask me again and I'll go into that. Absolutely. I completely agree. And there's actually a paper that I'll send out to you all where they address this issue in social and personal relationships. There's a paper 2 years ago or something like that. So yes, I will absolutely get to that. And so again, I'll get to this a little bit later too. You can distinguish dyads in more than one way too. That's really, really important. So if you have heterosexual couples, but you have one partner who has diabetes and one partner who's a caregiver, you can distinguish them in two different ways, across patient caregiver or across gender. And so how you distinguish them, again, needs to be theoretically driven. Because if your research question is about the mutual influence of how the caregiver's social control is affecting the health behavior of the person with diabetes, checking their A1C, diet, exercise, things like that, it makes no theoretical sense to distinguish them across gender. None whatsoever, because you're combining the effects and you're going to get a bunch of null results, most likely, right? Because you distinguish them in the wrong way. You can do older versus younger partner. You can do primary parent, secondary parent. There's any number of different ways you can distinguish people. So it needs to be theoretically justified, theoretically driven, right? And then we have what's called empirical indistinguishability or distinguishability. And that's where you empirically test whether or not your theory is supported, whether or not males and females are actually different, or maybe did you just think they were different, but in actuality, their means, their variances, and their covariances are identical, right? And so that's actually really important because, again, it goes back to theory, it goes back to power, it goes back to the way you analyze and estimate the model, right? And so, again, it's going to be really, really important to test empirical indistinguishability, and people just don't do it. Very rarely do I read a dyadic study where they actually test the ISAT model. It's called the ISAT model. where they actually test it. And so I don't really know whether or not they're distinguishable or not. All right, so here's again a more precise definition, more than my rambling on distinguishable dyads. And again, you have to have that variable in your data set. Otherwise, there's no way to actually assign them to A and B. Again, here are several different ways to distinguish folks. And then you have, again, indistinguishable dyads, same-sex partners, monozygotic twins, roommates, friends. Some of you do research and education. You might be interested in like social networks of friends. You have probably indistinguishable dyads if you have boys and girls who are friends with other boys and girls, right? Within that same sex. All right, so that is brief introduction into distinguishability, all right? And again, the concepts are going to be fairly simple here, but when we move into the analyses, they're really going to rear their head, and they're going to cause problems, or they're going to actually add a lot more depth to things that we are talking about and to aid in the development and refinement of theory. For the love of God, well, if you want to do a dyadic study, like think about that beforehand. Think about the questions you're going to ask. Think about how you want to collect the data. Think about the types of analyses you envision running. Because I've seen studies where they collect dyadic data and afterwards, not a single one of the measures or assessments was dyadic in nature. It was all individual. It was all psychopathology and personality. That's great, but is there like what question are you trying to answer with only asking individual level questions? So if you're only asking individual level variables, are you really saying that there's a mutual influence? Or are you just kind of tacking that on afterwards, which to me is going to lead you into a type 1 error realm because there's not a theoretical justification for it. So don't try to make your studies dyadic on the back end. Be intentional and be planful on the front end. So in that vein, a big aspect of creating a truly dyadic study is the idea of measurement. And so thinking back to, I don't know, 70, 80, 90 years, this is my favorite definition of measurement that I've ever come across is the principled assignment of numbers to observations according to rules. Real simple, real straightforward. What's the next logical question that we ask? What are the rules, right? And so in dyadic analyses, one of the rules is we need to consider the relationship between both dyad members and the level of the question. And we'll talk about that next, right? So there's any number of different measurement strategies. You got mixture modeling, classical test theory, IRT, and moderated nonlinear factor analysis, just to name a few. Again, this is my, essentially one slide introduction into measurement. Where I really want to spend my time is talking about levels of measurement, all right? So you have questions like the CESD. How often in the past week or 2 weeks have you felt hopeless? And then a person reports on their own level of hopelessness, right? So that is an individual level of measurement. I am measuring my own symptoms of depression, right? Then you have a partner level question, which is how supportive is your partner? So it's my individual perception, but it's about my partner. All right, so it's referencing somebody else. It's not referencing myself, but it's still not exactly like a dyadic question, right? A truly dyadic question is at the dyadic or relationship level when you're referencing the relationship. That's truly a dyadic question. So all things considered, I am happy in my relationship. The point of reference is the dyad, right? Whereas in the partner level, the point of reference is the actual partner. So yes, it kind of talks about kind of an interactive or a partner kind of effect, my perception of my partner and their perception of me, but is that getting at what's occurring between us? And the answer in my mind is kinda, maybe. I don't really know how to really make sense of that. And we'll actually see, and if we have time, I'll run through an example. We can look at factor loadings, because the factor loadings for relationship, dyad level, relationship level questions are going to be much higher. Perception-based questions, my partner is warm, my partner is supportive, they tend to be a little bit lower. All right.
I have a question. I don't know.
Yeah.
Sequence. So if you have, let's just say you have a research question, something like, I believe that one partner's depression can impact how satisfied their partner is in the relationship on like a general. Does that not work in this framework? In that case, it's like an individual measure predicting a partner's individual measure. Does that make sense in like an APIM framework, or is that just?
No, that absolutely works. My question to you, and the question was for those online, or about my level of depression impacting my partner's perception of relationship quality. My question to you would be, how are you conceptualizing relationship quality? Are you referencing an individual's perception of the relationship, or at the individual level, or is that at the dyadic level? How are you defining relationship quality? How are you operationalizing relationship quality? At what level is that occurring?
So something like the CSI that says something like, all things considered, I am satisfied with this relationship.
Yep.
To me, that's, the way that that's worded is like my own kind of global quality. It doesn't make sense to have that be predicted by like my partner's depression. So one partner's depression predicts another person's own perception of the global quality of the relationship. Does that work in this framework or not?
So you can do it either way. So you can have an individual's response on depression predict an individual's level response on a relationship quality variable in an APIM framework, or you can move into a hybrid format where you can have each partner's report of depression predict a common fate latent variable where each member's levels of depression uniquely contribute to what happens between the partners, what is shared between the partners, right? So that's, we won't get to that in this workshop, but you can absolutely do that. They're called hybrid models. And you can have a dyadic level construct, such as like dyadic coping, predicting each person's level of depression, which is a common fate actor partner hybrid model. Or you can have like the one you're describing as an actor partner common fate hybrid model, where my depression predicts what happens between us. My partner's depression predicts what happens between us. All right. Because if we think about it kind of theoretically, my depression might actually affect how we cope with stress as a couple. Right? That is kind of, that's that hybrid level. So that's why I was asking you, what's your level of relationship quality? Are you thinking about it at an individual level or at like a joint kind of dyad level? Is that making sense?
Yeah.
So here are just some examples of, I know I verbally gave them, but some more examples of just levels of measurement. And the reason that this is important is because in the APIM, you can do whatever you want with any of these. In a common fate model, you cannot do anything with individual. And to me, it's a little sketchy to do something at the partner level in the common fate model. You really need, in order to effectively run a common fate model, you need questions and assessments that occur at the dyadic level. What is shared between partners? What is common between partners? A construct that refers to what is going on between the individuals. It's not just how the individuals are existing together, but how do they play off of one another? Mm-hmm. So these are the keys. So when you're scouting out measures, read the questions and think, what is the unit of analysis here? All right. So me and Jordan and Matt Brosey just collected a bunch of data, and we collected the relationship attribution measure. That's about an individual's attribution. That I can't kind of create a dyad variable out of it. It's not a shared, there's not a shared kind of attribution that occurs in the relationship, right? It's a dyadic level variable. It's a dyadic level variable. It's how I interpret my partner's behavior, but that in and of itself is not a relationship variable, right? So you need to be really, really intentional around that. But I collected dyadic coping too, which is a relationship level variable. So again, this is what I'm talking about when planning a dyadic study. It's not just about the recruitment, it's about your measures even, right? So in dyadic data collection, you generally want to collect the same, use many of the same measures for both people. It doesn't really make a whole lot of sense to collect a PHQ-9 from one person and the CESD-10 from another. There's potential, maybe some concurrent validity stuff. I wouldn't do that. But you certainly can if you want. But collect the same variables from both partners. Be sure you're clearly assessing who the target is. What are you actually trying to get at? Right? And again, I want you to not just think about the level of measurement. I want you to picture your statistical model when you're looking at measures. What research question am I actually trying to answer? Is it a mutual influence question? Then self-referential, partner referential, or even dyad referential, all of those items are fine. But if I want to answer what's shared between partners or how partners change over time, how the quality of a marriage changes over time, that inherently is a dyadic level construct. And so you need to assess that construct in that manner, right? So here's an individual coping scale. This will be we'll get through these example measures and then we'll go on our first break. So when dealing with the problem, I spend time trying to understand what happened. When dealing with the problem, I try to see the positives of the situation, so on and so forth. So all of this is individual level coping, right? So we could not use this in a common fate model. We could use this in an actor partner model because how I cope might actually influence how happy my partner is. Because if I'm really, really good at coping, then my partner might be happier because I'm not, for lack of a better word, trauma dumping on them all the time, right? And they're not overwhelmed, okay? And if I'm really, really bad at coping, again, that process kind of happens and my partner's less happy and there's an effect there. There's clearly family system theory would support a type of model like that. But if we think about the dyadic coping inventory, how couples cope with stress and stress communication together, that's a very different construct altogether. All right. And so it's 37 items. So I only created a brief slide highlighting some of the items. And this is where read over some of the items from 5 to 15 and from 16 to 19. And what level of measurement is the dyadic coping inventory at these questions? What was that? Yeah, this is partner level. So that's kind of what irks me. Is this truly dyadic coping? No. This is my perception of my partner. And if you give this scale to my partner's perception of me. That's not dyadic coping to me. It's not dyadic coping in its truest authentic sense, right? So again, this is when my partners feel stressed. So this is how my partner communicates when he or she feeling stressed. So that's my perception of that. So this is alluding to an actor-partner interdependence model. This is my perception of how my partner communicates, right? So invariably, that's going to have an impact on me. When they're stressed out, how they communicate is going to have an impact on me. So you can't really, in my eyes, you can't use these measures in a common fate model to see how people are coping together, despite it being called the dyadic coping inventory. But what you can do is there's this beautiful subscale at the very end that does things a little differently. What is the level of measurement here? Yeah, it's dyad level, right? It's we try to cope, right? It's still my perception because there's no way around that, honestly. We're always getting at an individual's perception in some way, shape, and form, but it's my perception about what we are doing as a couple together. We engage in serious discussions. We help one another. We help each other. We are affectionate towards one another. This you can absolutely use in a common fate model or in an actor-partner interdependence model. I would say this really is a common fate variable. You probably shouldn't use it if you really want to assess the construct in its truest form, because if you think about it from like an actor-partner interdependence model, why would my partner's depression, being the IV, impact my belief about how we cope? And it's not even considering my partner's perception about how we cope. So to me, there's it kind of feels okay, but if the items are really focused on we, then let's measure it at that we level, right? That dyad level. Let's use a common fate model or use a common fate hybrid model, all right? And the last subscale is is a satisfaction subscale. What is the unit of analysis on this one?
Individual.
An individual? What tells you both? Okay. So to me, I have no idea. I really have no idea because it says as a couple. So that leads me to dyads. Then you read the question, I am satisfied with the support I receive. So that's in 36. And the way we deal with stress as a couple. So that 36, I don't even know how to answer that accurately because it's at the individual level in the STEM, the first part of it, and it's second level in the second part of the question. So essentially what this question is doing, it's conflating the individual level, the partner level, and the dyad level. And so to me, this is just nothing but measurement error. You're conflating two things that are operating at two different levels within the relationship. Not good. So don't ever use these questions because I don't even know what they're measuring because it's so confusing and we're getting contradictory information about what it is we're actually measuring, right? And by the way, satisfaction items, like, God help us, they give us no real information. Like, think about if you're a couples therapist and you ask them how satisfied are you in your relationship and they say a 7, well, what the hell does a 7 mean? So to me, it's the same thing. Why do let's look at the first 35 items that actually that actually measure information about stress communication processes rather than just saying how satisfied are you? To me, it doesn't really give us a whole lot when we think about that from like a clinical perspective. For researchers, it's really great because we can ask 3 or 4 items and we're good to go. But to me, I've been using the couple satisfaction index for 10 years. I still have no idea what it actually means. No idea. We just use it. It's a good measure. It's validated, IRT and all that. I still don't know, all things considered, how happy are you? What does that mean? So that's, again, a diatribe. Okay, we will take a 15-minute break and come back at 10:45 Central.